go to 0. So it means that you will lose individuals older than X from the population without necessarily compromising the persistence of the whole population, because those individuals won't contribute much to population growth. So it means that you have effectively a shortening of the life cycle due to climate change that you will never see in unstructured populations. So this diverging lag is not observed in unstructured population, something that can go on only in these heterogeneous populations. And the reason why you've got this negative feedback leading to the loss of some age classes is that if the lag in adaptation affecting some age classes is large, it means that you will have increased mortality at this age. And increased mortality at this age will decrease the strength of selection here through this elasticity and thus increase the maladaptation lag. And you've got this spiral of increasing maladaptation and higher mortality that could lead to the meltdown of a specific age class or a range of age classes. So it means that with climate change, what's going on is you've got this meltdown of the age classes. So the last age classes with reproduction will actually move back in the life cycle. So you've got this wall of death moving towards younger and younger ages, and will stop at some point, but it's really this shortening of the life cycle in a changing environment. So then I will describe a quite different situation. So the motivation for that is coming in part from studies like this. So this example study looked at this plant, and they found that climate change was favoring earlier flowering in this plant. And earlier flowering was associated with increased seed set under a warmer climate. But at the same time, if you flower earlier, you become more visible to herbivores. So we also found that those plants, there was an increased risk of grazing when they were earlier, so which decreased the survival probability. So you're here in a case where some change in trait that is connected to climate change has a positive effect on one fitness component, which is fecundity, and a negative effect on another fitness component, which is survival. So I wanted to model that, and so more generally, a lot of our understanding of some species distribution and relationship between traits and climate, like phenology. So phenology will affect the timing of different events in the life cycle, like birth or leaf senescence, and those will have different effects on fecundity parameters and survival that might be quite different, and then will be combined into population growth and demographic growth. So we had a very simple tree life cycle model, which is just a caricature basically, but we imagined that there was one immature stage, and those immature individuals could mature and become adults, then they could reproduce and grow more immature individuals, and then you could stay in this immature stage for a number of years and survive in the adult stage for a number of years. So thinking about phenology as a case study, what we thought would be reasonable assumptions is to assume that leafing date will affect immature survival mostly, because a young tree will be killed by frost or will be easily die out of carbon starvation or drought if it had too short a time to accumulate resources during the growing season. But the same events are unlikely to kill a mature adult tree that might be more resilient to this kind of persistence. But the fecundity of those adult trees might be sensitive to this kind of events affecting the timing of the life cycle. So if you set your leaves too early, and you've got the frost, you might lose your entire crop, or if you started photosynthesis too late, you will not have time to mature your fruit before the end of the season. So we imagine that in this case, immature and mature individuals will express the same phenotype, the same leafing date throughout their whole life, which is not exactly true in reality, but there might be conflicting selection effects of this trait on survival of immatures and reproduction of mature individuals. So again, we assume that there will be some Gaussian relationship with some optimal date favoring maximizing fecundity of adult trees and some maximizing the survival of young trees, and that both of those optima can change with climate warming. So using the same kind of framework, you can predict what would be then, in a constant environment, the optimal phenotype, the optimal living date that will do the best compromise between those two life history components. And actually, it's a simple weighted average between the optimum maximizing fecundity and the optimal trait value maximizing survival, with weights that depend on those same demographic elasticities that I showed you before, but here in the state structure model. So I don't show you them in detail, but for instance, I'm saying some illustration of some kind of intrusive prediction. If the rate of maturation of trees is increased, it means that you're going to spend less time in the immature stage, and so if you do that, if you increase the maturation rate and the juvenile period becomes shorter, then you will have stronger selection. You will have traits that maximizes fecundity rather than immature survival, because you don't spend time much selecting on immature survival anymore with this kind of life cycle. So what is also interesting with this kind of model is that actually those demographic weights, they evolve together with the life history traits. So for instance, the thing we did there, that we fixed the optimal date of living that would maximize fecundity, so it was constant, and we changed the optimal date maximizing juvenile survival. So if the difference between the two optima is not too big, you evolve a strategy that is intermediate between investing in survival and fecundity, but beyond a certain stage, if the difference becomes too big, you cannot actually do a good job of trying to maximize those life history traits. In this case, you invest in this prior set, you invest mostly into increasing fecundity and not investing much in juvenile survival. And this is because once juvenile survival becomes really poor, then the selection pressures in investing in these life stages becomes very weak as well. So now, if we looking at what's going on in changing climate for this life cycle, if you look at the lag in adaptation at equilibrium, it's very similar to what we had before. We have this lag that is measured now with this optimal date in a constant environment, which is a compromise between the optimum for fecundity and the optimum for survival. It depends on the rate of climate change, it depends on the genetic variance for immature individuals, and depends on this strength of selection which are affected by demographic weights. But what is more interesting is that, so it's basically really the same model. So here you see the 3 years, we simulate a change in survival optimum, fecundity optimum, and this is the best compromise between the two through time. And the population will evolve and lag behind this optimum, as it does in some unstructured population. But then the consequences for life history are interesting, because as you lag behind the best compromise strategy, you move away from the fecundity optimum, but you also get closer to the survival optimum. Not because it's good to invest more in survival in this environment, but just because you're lagging behind in terms of evolution, because of direction of evolution. And so if you look at the consequences for life history traits, what you find is that through time, in the changing climate, you will see a decline in fecundity, but you will see improvement in some other life history traits. And actually, I guess that if you would see that in data, you would think that, okay, under a new climate, I've got selection for a different life history strategy, and I see improvement of some life history traits, so it's a good thing. Actually, it's a bad thing. The population growth rate with this combination of traits is poorer than with the original combination of traits, which is lower survival and higher fecundity. It's just because it cannot track its environment that it's changing life history, not because it's a good thing to do so. So that's exactly what I said now. So improvement in this component, falling climate might not correspond to an adaptation, but correspond to a maladaptive response if you look at the complete life history trade-off. And it's reflecting actually slow evolution and not rapid evolution. So then, if we move on, can we parameterize those very abstract optical models of for concrete cases and get a better quantitative understanding of the challenges that species have to meet in the changing climate. So there's the option of empirically estimated selection gradients and traits, as was done in a number of cases. But what is frustrating about those is that those are kind of costly experiments to do, and they're rarely available for many populations across large spatial scales, like species range. Those estimates of selection gradients typically vary a lot among years, so it's difficult to have an idea about long-term trends of selection when you remove this noise, or if you take into account the regime of variation in selection. And a difficulty is that we cannot measure selection gradients in future climate, or you could experimentally simulate new climates, but you cannot necessarily do so all the time. So a lot of people have used the space for time paradigm to try to mimic climate change by moving population in some environment thought to mimic their future climate, but with many limitations there. So as a complementary approach, what we try to do is try to compute those selection gradients based on models, but based on models that are informed by our understanding of processes that affect the response to climate or the selection pressure for climate. So this is not an alternative, it's just something that might be complementary to those experimental approaches. So what we do is that we use this model that was developed by Isabelle Schwinn in Montpellier. And this model was aimed initially to predict tree species distribution based on a process-based model which would simulate the fitness of some average adult tree, and which was validated by, so it was fitted not using data on species distribution, it was fitted from data about the relationship between local climate and phenological traits and resistance traits. And then it was validated with external data about species distribution, trying to predict species limits for 15 different tree species in North America and Europe. So what the model does is that it predicts from the local climate the value of phenological traits and the value of resistance traits like cold endurance, and then from those traits you compute survival and production probabilities that are combined in some fitness measure. So what we did with this model is we played with it in a different way, which is instead of having local climate predicting the value of phenological traits based on plasticity, we just varied those traits artificially to see what would be the consequences of varying those traits on the fitness. So here you've got an example. So for instance, here you've got, so what we do is we, instead of having leafing date changing with climate, depending on the reaction norms that have been fitted to data, we just fix the leafing date and compute what will be the predicted fitness in every location of Europe for this oak species. So this is the map of fitness you would have with red color showing high fitness and blue color showing low fitness. If the leafing date was fixed at 16 Julian days, 100 Julian days, and 150 Julian days. So if you do that, you can actually reconstruct some kind of fitness landscape or relationship between trait and fitness, similar to the theoretical one I showed you before. And so for different locations, you can actually predict what is the relationship between fitness or fecundity or survival and birth date. And so you can show that we've got different optimal phenotypes in different locations, but also different shapes of selection. So you can infer optimal phenotypes, strengths of selection, how they change in space, and you can also see how they change in time by using climatic time series or predicted climates. This is just one example of such an exercise. So it's just one locality with oak and oak population. And we predict it was the optimal leafing date in Julian days for that population for years, so either years in the historical period, but also years that are projected from climate scenarios, so until 2100. And so one thing that we noticed is that you've got fluctuation, this optimal value from year to year, but you've got all those events with very bizarre optimal, like negative dates, which is a bit bizarre from a logical point of view. But actually, all those points correspond to very strong, extreme directional selection for precocity. So when the optimal date is negative, it means that actually within the range of feasible dates, there's no date that maximizes fitness. So there's very strong selection to push you towards precocity, but you don't see any evidence of stabilizing selection in those years. So if you remove those, and so what you see is that you seem to be an increased frequency of those very strong, extreme, unusual selection events in future climates. If you exclude such extreme, you can compute such things like how much, so the kind of K parameter had in my previous model, how much the optimal phenotype changes per year. So here we estimate that to be minus 0.15 days per year. And then what I found interesting is that there are many years in this modeling exercise where actually there's no selection going on in the population, because we predict that every phenotype within the range that we know exists has a fitness of 0. So it's not a fitness of 0, it's a fecundity of 0. So I mean, for a tree, it doesn't mean much necessarily that 1 year you have complete failure of reproduction, because you're going to have many years with reproduction, and oak trees are known for nesting, so they actually have very few years where they have effective reproduction. It still means that if you're sampling environmental variation through time, there are many years where selection is not effective because there's no fitness differential in the population, because everybody is just doing so poorly. And this is clearly increasing under projected climatic scenarios. So this is something that models that I've just showed before are not taking into account at all. So the perspective of this work is that, so we could, what we would like to do now is use those models to contrast selection pressures acting on different life history traits and stages, and contrasting selection acting on survival and fecundity, for instance. One thing that this exercise suggested is that maybe the way we're simulating or mimicking the effect of climate change is not the right way, because we should actually introduce in those models not only a still progressively changing environment, but really look at those role of extreme selective events. Do they have a big effect on those populations with state structure or not? And one thing that we are working on at the moment is trying to look at what is the role of phenotypic plasticity in this context as well. Before I finish, I want to thank all the students and colleagues that worked on this project with me. So Linnea Sandel and Mathilde Grenier were 2 master students that worked on this model. Olivier Coteau during his PhD, Anne Dupuquier during her postdoc, and with Miguel Chevin and Isabelle Schwinn, colleagues from Montpellier that worked together with me on this project. Thank you.
Questions?
Yeah.
Thanks for the very nice talk. I have a question about your model with age structure.
Yeah.
If you had parental care in the organism, how do you think the result would change with regard to how climate change?
There's been models about that, so concerned specifically with humans, and concerned about this wall of death story. So if you have extensive parental care, it's actually making you actually contributing to your, it means that somehow your effective fecundity or your contribution to fecundity is not 0 after the last age of reproduction, because you have to include the period of parental care in there. So it's actually making it go slower at the end. But it's, what I want to point at is any life cycle, even with increasing fecundity with age, even with no last age at reproduction, will have declining strengths of selection with age, because this is a property simply of of mortality. You've got less individuals of greater age than small age. So this quantity that Hamilton computed is always decreasing with age, whatever the life cycle. But then it could do so fast or slow, depending on the details of the life cycle. And then it doesn't mean that you expect senescence to evolve all the time, because this is one part, the strength of selection. But then if you have a gene that has effect, so it then depends on what the gene are doing on different life districts at different ages. So there are trade-off structures or genetic effect that will predict actually the evolution of negative senescence, so that you will actually evolve higher survival in higher ages. But it depends on trade-offs that you put in. But it's still, what is true to all life cycle is the strength of selection will decline with age, and then how it will combine with genetic variation may predict different things in terms of evolution of life histories. Yes, Graham?
The model of a changing environment is a model of a deteriorating environment. Things always get worse.
It's not getting worse, it's changing. It's not, if you could be adapted to this environment, you will achieve the same population growth rate than in the ancestral environment. So you just have a lower, in this model, you have a lower fitness because the environment does not stop changing. It's changing all the time, so you never can, catch it. So you're always late.
As the environment changes or deteriorates in that way, then the development-specific mortality shifts to the left, producing what we call more rapid size.
Yeah.
Would the model work, and the models you analyze are one-dimensional, would they work equally well in any number of dimensions?
I think so. We did that with a different model, looking at multivariate selection on many different traits, and environment being in multivariate space. And basically you end up with a very similar equation. Just that you have to shift everything in this multivariate writing, but you still have a lag that could be different for different combination of traits, but I don't think it will change much.
So let's take the critical view of the world, which is that in some multidimensional way, the environment is continually deteriorating.
Yeah.
If your theory is correct, that means that the senescence is continually increasing too. And then after a certain period of time, everything will die immediately it becomes born. How do you escape from that pattern?
I don't think the environment is always, so the environment might be not always changing at the same rate, maybe?
It wouldn't matter in your models. You can change at different rates, but it's always deteriorating in the sense that you always have lag.
I didn't think about that. So,
But if the optimum stops moving, then the population catches up, and then all of a sudden all individuals.
And moving in multidimensional space.
so okay. So what? Maybe one answer to your question that we also model a case of fluctuating selection. So it's also an environment that keeps moving in one direction or another. So what we find is that indeed in this case as well, you have higher lag load for older age classes. But it doesn't mean that you always, so you still reach a stable state given some regime of variation. So it means that what it just says is that this changing selection could contribute to a part of the aging patterns we see in population. Doesn't mean that it's always putting more aging and more aging and more aging. It's just that there's still a stable life history in this environment that are fluctuating all the time. It just means that part of the increased mortality in old individuals might be due to the fact that traits that determine the performance are lagging behind more than traits that are expressed for young individuals. So it's just another additional explanation for aging. That doesn't mean that you've got this meltdown that will keep on going. Even in this changing environment here, you lose some age classes sometime if the rate of change is very fast, but you don't lose at all, and you don't evolve. It's not like evolving in an annual life cycle. It stops at some point still. It stops at the point where selection pressure are strong enough to keep the lag in check. So, and also what is interesting is that in the fluctuating environment, sometimes actually it's better. Genes that are evolving slow because they are expressed late in life actually have a smaller lag load. Because this is what's happening when the environment is changing very fast. So actually it's good not to respond too fast to selection because the next generation selection is going to take you somewhere completely different. So if you don't evolve, if you evolve slowly, you're actually achieving Beta means fitness, but it's only, and this was described by Langley and Shannon, and also looking at the effect of genetic variance. In environment that fluctuate very, very fast, sometimes it's actually good not to respond to selection and keep the same phenotype or genotype from year to year because there's no predictability in the change in the environment. So sometimes it's just reverse, it makes the old ones better.
Yeah, we need another question.
Okay, so if you look at the narrative of your entire talk, you start out by saying we don't have much evidence today for in the field at least,
Yeah.
for evolutionary and adaptive responses to climate change. And then you show us 3 very elegant pieces of theory that suggest we're expecting loads of various kinds that mean it's tough for evolution to keep up with the pace of climate change.
Yeah.
That we have in the middle section, what was that's right, evolution could be maladaptive, even though it looks adaptive. And in the third case, we have these, if we take into account the extremes, we can get to these fecundities of 0, where there is no possible selective response.
Mm.
So this leads to a conclusion that evolution is not going to help us much in the near future. And is that something that you hold?
So, well, that's what I want to qualify.
When and how and where?
Yeah, so the part of this project is related with people that work in forestry.
Yeah.
And so it's true that there's argument that trees have a lot of genetic variation for traits and for local, for climate adaptation. And there is evidence that they were able to locally adapt to many pressures despite their very long generation time and everything. But what I want to do is do a more quantitative model to show, despite this very high genetic variation, if you take into account the life history and the life cycle and everything, can they really adapt to a changing climate, which is ridiculous in terms of rate of change compared to generation time. So I just want to be quantitative about that. I don't want to say that evolution is in general not relevant for the response to climate change, because I think maybe in some organisms it is, but I think it's difficult, and I certainly don't want to say that there's everywhere the potential to adapt to fast changing environments.
So I think what Andy's saying, which then echoes what Graham and Ophélie work on, is that we should all stop studying evolutionary rescue.
No,
Hopeless.
no, it's not.
He wants us to admit.
Let's have wine and cheese rescue. Now, thank you.